Our next goal is to now consider the case where we have a flat plate, which is called a lamina, with a uniform density rho, and we can look at that flat plate as occupying a certain region R of the xy plane. And to imagine here, we've got some region R here in the xy plane, and we can rely on two simple principles to help us determine where the center of mass of this region can be located. First is the symmetry principle, which says that if I have a region which is symmetric, for instance, say a rectangle, then the center of mass is going to lie in the middle of that rectangle, for instance, here. So I can just locate any line of symmetry in the region, and we know the center of mass must lie on that line of symmetry. Okay, so rectangles are conveniently very symmetric, so locating the center of mass for a rectangle would be locating where the midpoint of that rectangle is. Okay, and the second principle says that we can decompose a region into smaller regions and then use the sum of the point masses, where for instance, if I take the region R here and break it up into smaller sections, I can locate the center of mass in each of these smaller sections and then treat the entire section as if it were a point mass located at the center of mass. So then finding the center of mass of this region is a matter of finding the center of mass of these individual point masses. So in this case, that'll be essentially how we break a region down. First, we'll subdivide it into subintervals and then use approximating rectangles under the curve, where of course, because it's a rectangle, the center of mass is going to lie at the midpoint of that rectangle. So let's take, for instance, the ith rectangle here. The center of mass there will be located in the midpoint of that ith rectangle. So it'll be located in the midpoint between xi minus 1 and xi. So denote that by xi bar. And the y-coordinate would be halfway between 0 and f of xi bar. And so we would say it's 1/2 xi bar. So here the center of mass is located at xi bar, comma 1/2 f of xi bar. Okay, so if we do that for all of these rectangles, they're each going to have a different center of mass. We can then use the principle that we had in the point mass case to find the center of mass among all these separate center masses. Okay, so therefore we know that the mass of our plate here, let's say we're looking at the ith plate, we know that the entire area of that ith rectangle would be delta x times f of xi. Times the density, which we're calling rho. So that gives us the mass of that ith plate. So then mi xi would be rho f of xi times x times delta x. So then summing up all of those gives me my my. Rho xi bar f of xi bar delta x. And this is now a Riemann sum that can be written as the integral from a to b of f of x. So similarly, we can do miyi to get the moments about the x-axis. So using our same mi here, delta x f of xi rho. And the yi would be f of xi. But it's 1/2, because remember that the y-coordinate of our center of mass is 1/2 of f of xi bar. Okay, so that gives us then delta x 1/2 f of xi squared times rho. So taking the sum of those gives us our moment mx, and then taking the limit as n goes to infinity, we get the Riemann sum for the integral from a to b of 1/2 f of x squared dx. And then the mass of the plate will just be rho times the area of the plate. Okay, so putting those pieces together, then we can get right, m. So for x bar, we can do my over m, which is integral from a to b rho x f of x dx over rho times a, the area. And then notice that the density divides. So the density of the plate does not actually play a role in our formula. And then for y bar, it's the same. It's mx over m. So the 1/2 integral from a to b rho f of x squared over rho a. And again, the density rho divides out. And so that gives us our formula for the x and y coordinate of our centroid. Let's try this out with an example. Find this center of mass of a semicircular plate of radius r. So I'm going to draw my semicircular plate of radius r, which can be given by the equation y equals the square root of r squared minus x squared. We can use the symmetry principle here to notice that because it's symmetric about the x-axis, we know the x-coordinate of our center of mass has to lie on the y-axis. It's probably going to be somewhere around there. So by symmetry principle, we know that x bar equals 0. Okay, so we don't need to worry about computing that one. Let's focus on computing y bar. So we know it'll be 1 over a, and then integral from negative r to r, 1/2, and then our f of x is r squared minus x squared, squared. And because it's a semi-circular plate, we know that the area of a semicircle is pi r squared. So this will be 1/2 of pi r squared. Here when I square the square root, it just becomes r squared minus x squared. Notice here I can simplify here the 1/2 with the 2 there. Okay. I can also use some symmetry here as well, because we notice that this is an even function, so integrating from negative r to r is equal to 2 times the integral from 0 to r. Okay, so exploiting the even symmetry in the function here. So we got 2 over pi r squared. And then integrating here, we get r squared times x minus 1 over 3 x cubed, evaluated from 0 to r. So that'll be r cubed minus 1 over 3 r cubed. So that'll be 2 over pi r squared times 2 over 3 r cubed. And then here, r squared divides with r squared here, leaving me with one more factor of r. So we have 4r over 3 pi. Would be where the y-coordinate of our centroid is located. So in this case, x bar, y bar will be the point 0, 4r over 3 pi.